Okay, have a look. So a quick review from yesterday. Let me have everybody phones away, earbuds, all that stuff needs to be away for now. It may get a little time to work at the end, and then you can listen to music when you're working. That's no problem. Okay, so let's go back and review the stuff we talked about yesterday, subsets of real numbers. Do you remember, and you may not, do you remember what letters, or what letters we gave to those sets? Yes, ma'am.
Irrational was Q, and apostrophe rational was Q, integers was I, linears was W, and rational was
Okay, good. So we had N for natural numbers, capital W for whole numbers. Integers we said was I, but really, so that works. But really the one that probably most books will have is Z, capital Z. So either one of those for today is fine. Rational numbers, for some reason we called Q, and the irrational numbers we called Q prime. So when you see that little hash mark up there, it kind of looks like an apostrophe, but in math we call it a prime. All right, and that's going to be important. We're going to use those in a second. For examples, let's just write down, see if you can, without looking at your notes, see if you can remember this. How did we define the set of natural numbers? So I'm going to start off with my set notation, right? And what goes inside that set? Yes, ma'am.
We can have this up there.
Go ahead, yeah.
1, 2, 3,
And then
4, 5.
it would just go, and they'd go forever, wouldn't it? So how do we represent it? It just continues?
The W's.
Good. Dot, dot, dot. Okay, it looks just perfect. What about whole numbers? What's the only thing extra we add to whole numbers? Yes. 0. Good. So the same stuff, only we're adding a 0 there. How about integers? What's extra there? Okay, good. Negative natural numbers. Right, so we'll go. Now we've got to continue the pattern in both directions, in the negative direction and the positive direction. So we got 0 in the middle, go 1, 2, 3, on forever in the positive direction. We'll also go backwards. Negative 1, negative 2, and I ran out of space. But you get the idea, right? So it goes forever. What about the rational numbers? So these were fractions, good. So how did we had kind of a fancy way of saying the fractions. What do we say? Yes, ma'am.
It's M is over N.
Okay.
M in integers and not
Okay, good. So we said the way a mathematician, that's you guys now, the way you would read this would be the set of M divided by N where or such that, right? That's that conditional bar. Such that M is an integer, N is an integer, and N is not equal to 0, right? There is a better way to say all that stuff, too. One way, we could take all that stuff that I just wrote in red, and this, tell me if you like this better. I know I do. The set of all N divided by N such that if I want to say M is an integer, here's an easier way of doing that. This symbol right here means is an element of. Or is a part of. So like a set, for example. So we could say M is an element of, how did we say the set of integers again? What was our symbol for that? Z. Or I mean, I, it could be I, but usually it's Z. Okay? And then we want to say all of these things at the same time. So in math, there's a tricky way of saying and. This is our symbol for and. Okay? That means literally and. So M is an element of the set of integers, and N is an element of the set of integers. And finally we had n does not equal 0. So we talked about how in math, mathematicians find ways to make things concise, right? We use symbols a lot. So just those few little symbols says all of that stuff, okay? This element, you'll eventually we'll use this in a little bit. This element business, it's not this. It's easy to confuse. It's not like a cursive E. It's like a half circle with a kind of a line sticking out of it, right? And it's an E for element. But that's how we always write it. Okay? What about the last one? Irrationals. What do we say about those? How do we define the set of irrationals? So rationals are fractions. Irrationals are what? Pi is an example. Okay. Square root of 2. Those are all good examples. How would we define the set? Like, if I want to use that fancy set notation, what would I do? The set of, remember what we wrote yesterday? Didn't we use H? The set of H such that, what about H? What do we say about H? So H is what? For it to be irrational. This was a weird one. And it's sometimes it's easy to overlook the importance of this, but all of these other ones were related to each other, weren't they? They all followed patterns, and the smaller ones were subsets of the bigger ones. Are any of these subsets of Q prime, the irrationals? No, they're not, right? The irrationals were separate. They were just separated off from all the other stuff. The only way we can really define an irrational is that it is not, because that's what IR means, opposite of, right? It's not rational. So we're going to take the set of all H's where H is not rational. Okay, there's a better way to do that one also. There's a shorter way. So this one we could take a shortcut and we could write it like this. We could say the set of H such that, what do you think? If I want to say that something like, in this last example, n was an integer, we said n is an element of the integers. It's a part of the set of integers. How do you suppose I would say it's not a part of the set, or it's not an element of the set? Any ideas? How did we say, like when we say we want something to be not equal, what do we do to change that equal sign to a not equal sign? You can put a slash through it, right? So how do you think I would say H is not an element of, okay, I'm just going to do my element of and put a slash through it. So it's not an element of Q, set of the rationals, right? Everything else that's left over, that becomes what we call the irrationals. Okay? I think what helps with this is to put it into a diagram, a set diagram or a Venn diagram. Sometimes these are called Venn diagrams. Not a big deal, but just so you've seen the word. So let's assume that this box up here is the set of all real numbers. Call it R. That's that capital R we reserve for real numbers. Where am I going to put these other symbols then? How are they going to fit inside this box? Everything we've talked about, they're all subsets of real numbers. Like where would the n go? It's got to go in the smallest one, doesn't it? This smallest one, because it's a subset of a bunch of other things. So there's n, right? Counting numbers. What's next? W. Okay, so W would go here, wouldn't it? Because now we've got all this stuff, but we're also including one extra element, which is 0. So we need a little bit bigger set for that, right? Now what? I or Z, either one. There's our integers, right? That's a bigger set that includes the others. And then finally, Q. Okay. The rationals include the integers and everything else below them. What about this guy over here? What do you suppose that must be? Okay, now notice that's separate. Nothing shared there, right? They're separate sets completely. Okay, make sense? All right, let's just try a couple examples. We don't have to do all of these. Let's do some. So how about number 1? Our goal is to name all the sets to which that value belongs. Right? What's a good strategy for this? Starting from, say it again? Okay, starting from the smallest set that it belongs to, and then everything that all the other, call them supersets, all the other sets that include that one would get included also, right? So what about this one? What's the smallest set that one includes? Not natural. How come that's not a natural number? Oh, it's negative. Okay. Integers. Okay, so we know that it would be included in the set of integers. So if it's an integer, what else must it be for sure? It's got to be rational. Okay? And then we could even go maybe one step further. Real. Yeah, we could even, they're all real numbers, aren't they? That'll go in all of these. Okay, what about number 4? What's the smallest one that is? Okay, it's natural. It's written as a fraction. So it's a little tricky. It's trying to throw you off and maybe make you say rationals, right? But if we simplify this, 24 divided by 8 is what? 3. Okay, now it's easier. So now it's everything, isn't it? N, W, Z, Q, R, right? What about 7? Okay, irrational, because it's got pi's in it? I get why you say that. Somebody else have a different answer? What is it? It's 0. What would 0 be then? So what's the smallest 0 would belong to? I heard it. Whole numbers, right? Okay, so if it's a whole number, then it's an integer. If it's an integer, then it's a rational number. If it's a rational number, it's a real number, right? What about, let's see, number 2? Number 2. It's irrational, isn't it? How do you know? Say it again. Comes out as a decimal. It's not. So the square root of 30 is not pretty. 30 is not a perfect square. Now, if that had been 25, it'd be set, right? Square root of 25 is just 5, and so that's natural all the way on up, right? But this one doesn't simplify, and so it's going to be q prime, and then what else? Real. Okay. What about? How about number 9? What's the bar mean? Okay, so if it's written as a decimal and it's repeating, what's that telling you? It's rational, isn't it? Okay, but that's the best we can do. That's the smallest set because that is clearly not an integer, is it? Right. So all we can do on this one is rational, and then it's all, of course, it's real. All right, I think we're good. Okay, so let's move on. I want to look at just one quick topic today, and then tomorrow we'll take a break from math for a day. We'll do some different stuff. So I want to talk about the properties of equality for real numbers. So sometimes things that we do in math or otherwise require a certain order, right? And we'll start talking more and more about that. We're going to do not Monday, you can take Monday off. It's been a great week. Next Tuesday, we'll start talking about order of operations and simplifying stuff. And then there is a prescribed order we have to follow. But sometimes it's not that way. Sometimes we don't have to worry about order. And that's handy when that's the case. Sometimes we can make use of that. Now, the commutative properties. Okay, so does anybody remember off the top of their head what the commutative properties tell us? What's the commutative property of addition? Do you remember? They can flip back and forth. Good. Here's a way to remember that. When you commute to your job later in life, when you commute to your job, what do? You start at your house in the morning, and what do? You change position, you go to work. And then in the evening, you change position and go from work back to home. So to commute means to flip or exchange, right? So that's an easy way to think about it. The commutative property of addition just says that if I've got two numbers, A and B, and I'm going to call them A and B, I don't want to pin myself down to specific numbers. These could represent any numbers, right? A plus B is the very same thing as B plus A. For example, it doesn't matter if I say negative 2 plus 7 or 7 plus negative 2, the answer is 5, right? So there's the commutative property of addition. Multiplication works the same way. A times B is B times A. Doesn't matter the order in which you multiply it. Negative 11 times negative 4 is the same as negative 4 times negative 11, right? No big deal. Okay, there is a point, though, that maybe wasn't emphasized before, maybe you don't remember. What about subtraction? Is there a commutative property of subtraction? Let's try it. See if it works. Like if we try 17 and 5, is 17 minus 5 the same as 5 minus 17? No, it's not. So you cannot commute with subtraction. Same thing with division. 20 divided by 5 is very different than 5 divided by 20, right? So it doesn't work for subtraction or division, only multiplication and addition, right? Okay. So how about associative properties? Okay, what's it mean to associate? The people you associate with are what? People you communicate with, sure. People, are you gonna tend to hang out with people that you associate with, or people you don't associate with? Associate with. So those are the people you group yourself with, right? So this is a grouping thing. Associative property. Who do you like? If you talk about law associates, a bunch of lawyers that work together in the same building are associates, right? They group themselves in the same building. So the associative property of multiplication or addition just tells us that we can change the order around in which we do these operations, addition or multiplication. So let's take an example with multiplication. It tells us something like this. If I'm multiplying A times B times C, I can either group the B times C or I can group the A times B. There's something that you take for granted, but I want to emphasize here. When you multiply things, let's take, you do this for me. Let's warm up our brains a little bit. So tell me, what's that equal to? What's 3 times 4 times 5? 60. Okay, how'd you get that? Somebody raise your hand and help me out here. What'd you do? Yes, sir. Okay, so one thing you could do is you could multiply 3 times 4 and get 12, and then multiply that by 5. Okay, anybody do anything different? What'd you do, Alex? Yeah, and that's probably what I would do, because 4 times 5, 20 is easy to multiply, right? And they both work. But 4 times 5 is 20, times 3 is also 60. And what's the other one I could actually do? 3 times 5 is 15 times 4. There's an important point there. How many times do you have to multiply to get this thing? Well, no. Y'all told me 2 things, right? You have to do it twice. Because you can only multiply things in pairs. You can't multiply 3 things all at once. It's just the definition of multiplication. It's 2 at a time, right? 3 groups of 4, and then 5 groups of that result, for example, right? So you have to break things down into steps, 2 at a time steps. It just doesn't matter which 2 you choose first, okay? Same thing, obviously, for addition. Well, same example we used, really. So if we're adding 3 things up, we have to add them 2 at a time. So if we're adding A plus B plus C, we can take B plus C first, get an answer, add A to that, or A plus B first, then add C to that result. Doesn't make any difference. Okay? Obviously, that's going to work. What about subtraction? Does it work for subtraction? Let's try it. So if I've got the numbers 8 minus 3 minus 15. If I group the 3 minus 15, I get 8 minus negative 12. If I subtract a negative, that's adding, right? so I get 20. What if I group the first two together? 8 minus 3 is 5, minus 15 is negative 10, not the same. Right? So once again, it doesn't work for subtraction. Suppose it works for division? No. Pattern you're seeing. None of this stuff works for subtraction or division, only addition and multiplication. All right? Okay, how about this? Distributive, time to get up, there you go. Distributive property, you know this one, right? There's only one point I want to make on this. Distributive property you do all the time. There's an example, right? If we have A times the quantity B plus C. Whenever we say the words, hopefully you've heard this before, but if you haven't, oh well, now you heard it. When I say the quantity B plus C, what does that imply? Later on we might even have other things in addition. If I say the quantity blah, 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 what am I saying about blah, blah, blah? The quantity means, it goes in parentheses, in grouping symbols, right? It's grouped into usually parentheses, but it could be something else also, right? So we'd say, question? So A times the quantity B plus C is the same thing. I could distribute the A. That's the same thing as saying A times B plus A times C. You know that, right? You've done that lots of times. Here's an example. If we have 4 times the quantity 12 plus negative 7, I could distribute the 4 to both parts, and I get my answer, right? Here's the one thing I want to point out, though. This is a common mistake. Sometimes people want to do the opposite. Okay, what about that? Does that work? If I have 6 plus 3 times 5, can I add 6 to both the 3 and the 5 and then multiply? Can't. How come? I get a different result that's wrong. Why do you suppose that that order doesn't work, but the top order did? Do you guys remember any specific order that you have to do things in when you're doing arithmetic? Okay, good. Yeah, PEMDAS, right? Order of operations. Talk about that next week. But we're not following the right order when we do this. Okay? All right, one last little thing on this guy I want to show you. So this top one, we could, I guess technically we could do some distribution there, but how would you probably do that top problem? If I told you to simplify that and just give me one number, what's that all equal to? What would you probably do? You're going to get, okay, you get 4 for an answer. How'd you get that? You probably didn't distribute anything. What'd you probably do first? 5 plus 3. We just used order of operations. So inside the parentheses, we simplified that to 12 minus 8, and 12 minus 8 is 4. That's pretty easy, right? Sometimes, though, you can't do that, like down here. You can't combine the x and the 3. They're not like terms, right? So here we do have to distribute. How would you do that one? Distribute the, well, not the x. What are we distributing? The negative. Okay, and that's fine. You can distribute the negative. You probably all know what we mean when we say that, right? If I distribute the negative, what am I going to get? 12 minus x minus 3, and so that's going to give us, what? If I combine like terms, what's 12 minus 3? So I end up with 9 minus x. That's fine. That's a good shortcut. Technically, I want to show you what you actually did. What you actually did, if you start off with 12 minus x plus 3, what are you really distributing when you distribute a negative? Negative 1. Yeah, this is the same thing as saying 12 plus negative 1 times x plus 3, right? And so technically, you're really distributing the negative 1, but you don't have to write it out like that. This is I would do it this way, right? We know what we mean, but I just want to make sure we draw those connections. All right, so identity properties. Very easy, but I want to point something out to you here. So what's your identity? Think about your identity as a person. What's that mean? Who you are. Yeah, who you are. So your identity as a person is who you are. It's the kinds of values that could be placed on you. They're probably not number values, but other values, right? Well, identity means the same thing in math. The identity property of addition, all that's asking us to do is we want to we want to figure out what's the number that I could add to something and have the identity stay the same, like not be changed. In other words, we say, what number could we add and preserve the identity of something? 0. Okay, so very simple. So we say that there's a unique number then, the identity number for addition, we could call it, sometimes we call it the additive identity. Either one is fine, and it's 0. Anytime I add 0 to something, I get back what I started with. That's the whole point. What would that number be for multiplication? 1. Okay, so we multiply by 1 and we get the same thing back. Good. Okay, so that's easy, but that's connected to, and it's easier to remember if you think about it this way. I'm going to tell you this lots of times this year. I don't want you to remember stuff. If you remember stuff, you're just going to remember facts you're going to forget. I once knew, and I'm sure, I think at one point I had to know all the state capitals. I probably know about 6 of them now. I don't know very many of them at all. Why did I forget those? Because they're just individual facts. They're not strongly connected in your brain. It's a low level of learning and it goes away in a hurry. So anything you memorize in here, you're just going to forget. Guaranteed. Instead, it's always better when you're learning things. And this is one of the best pieces of advice I can give you going into college. If you can remember stuff in a way that's higher level learning. So a lot of times throughout the class, we'll do things like if we talk about the distance formula. You're not going to remember the distance formula. You're going to forget that. But I could draw you a picture on the board that you could look at and say, okay, now that makes sense. All you have to do is draw that picture for yourself on a piece of paper, and you can come up with the distance formula in a minute. And then you'll have it. You didn't remember what it was, but the picture is a higher level thinking. There's more stuff going on that you can relate to, and that you'll keep, right? So same thing here. The identity properties, identity is pretty easy, right? You know, we want to keep the identity the same. We all get that. But the properties that go with this are the inverse properties, and you'll forget things. If you just remember them, you'll forget them. But the inverse properties, like for addition, the inverse property just seeks to, you're going to fill in the blank. Here's what the inverse property does. We want to know what would we add to a number A, if we want to get the answer that's equal to its identity, which we already told me was 0, right? So that's how inverse and identity, they both start with I, they go together. Okay, the inverse is what you're going to add to something to get the additive identity 0. Well, what would I add to A to get 0? Negative, whatever the number is, so call it negative A. So what's our word for that? If A is 3, what's negative A? Negative 3. So its inverse would be negative 3. If A is negative pi, what's its inverse? Pi. So what's a more specific word for that? Opposites. Additive inverses are just opposites. Okay? For multiplication, our strategy is going to be the same, only this time we're multiplying. So what answer do we want to get? We multiply by the multiplicative inverse for multiplication. What should the answer be? 1, because that's the identity for multiplication. So what do I multiply A by to get 1? That's a little tricky. What would I multiply 2 by to get 1? No, 2 times 2 is 4. 2 times what? I'll give you a hint. 2 is the same as 2 over 1. What could I multiply if I've got 2 over 1 times what equals 1? 1/2. Yeah. If I take 1/2, look what happens. The 2's cancel and the 1's cancel, and I just get 1 over 1, right? What do we call that? If A is a number, 1 over A is its what? Reciprocal, right? We're just going to flip the fraction, okay? So what's the reciprocal of, or the added, or multiplicative inverse? Same thing as reciprocal for 2/3. 3/2. What about reciprocal of negative 5/7? Is it 7/5 or is it negative 7/5? If I flip negative 7/5, I'm still going to have a negative fraction, right? Everybody agree? So it'd be negative 7 kids. Okay, good. All right, I think we're good. Here's just a summary. We just went through all this stuff. Why don't you, we'll let you go to work on this. Right, so the purple assignment, that's what I'll collect on Tuesday. Okay, the green one's just for your notes. Purple one I will collect. Say it again. Tomorrow I'm gonna take a break from this and we're just gonna, oh, okay. Don't miss it. Yeah, I always won't see one miss. You won't miss anything. No teaching.